Last talk in the last session, so I'll try to speed things up that you can all catch your plane. But for now, put yourself in the shoes of this network operator. All of a sudden, you get an alert that the egress in New York is reaching its maximum capacity. You want to relieve some of the burden from New York, and you ask yourself, where's all of this traffic leaving in New York coming from? So to answer this question, you look at the forwarding state to understand where the traffic is going through. You look at the traffic statistics to understand which traffic is actually present in the network. And in the end, you can identify the few important destinations which you want to reroute. Now, as you can imagine, this can be a lot of data. At New York, there could be thousands of prefixes reachable. And out of those prefixes, only a subset you can actually reroute because only a subset has multiple egresses available. And also, a subset of those destinations might actually only carry traffic. So you see, the challenge here lies in going from a lot of data to a few key high-level insights to a few destinations which you reroute. Now, answering this question, understanding how the network behaves can take a lot of time. And as a network operator, you're under pressure because you need to react fast, right? Your network is a critical infrastructure, and your customers will quickly complain if something doesn't work. In addition, networks get more and more complex, so you have more peerings in more different locations, you have a lot of routers, and this creates a huge tension, a burden on the network operator. So wouldn't it be nice if the network operator could skip this step of trying to understand what the network does and go directly to controlling the network? So what if the network operator could simply ask the question, where is the traffic leaving in New York coming from, and automatically get an answer? So in this talk, I present to you Net2Text. Net2Text is a system that assists the network operator in understanding the network forwarding behavior. It does so by automatically extracting the high-level insights from the low-level data, and does this in a timely manner. So you can think of it as a chatbot. You type your message, where's the traffic leaving in New York coming from? You enter your question, Net2Text takes your question, starts processing the data, and provides you with an answer. In this case, the traffic enters most in Philadelphia and goes to YouTube and Netflix. So as a network operator, you reroute this, and you hope you can relieve some of the burden on New York. So Net2Text goes from question to answer. And from question to answer, we go through 4 steps. First of all, we need to understand what your question is actually about. Then Net2Text needs to retrieve the data which is pertaining to this question. In the next step, extract the high-level insights, for example, the destinations to reroute, and then map it back to natural language. So let's look at all of these boxes in a bit more detail. To understand what the operator wants, we first split up the question into tokens. So basically the words of the question. And we try to identify the key tokens in this question. In this case, it's Google and New York, so an organization and a router. To understand the meaning of these words, we also look at the surrounding words. Google, we know it's a destination of the traffic, but the router, we only know that it's an egress thanks to the word to New York. So these two make up the traffic identifier. They tell us what the question is actually about. On the other hand, we also need to understand what kind of an answer the operator expects. And this is the query type. Here we have a how, so the operator wants an explanation of what is going on. At the moment, we support 4 query types, so we're a bit restricted in the questions you can ask, or you can quite easily ask a question which we cannot understand, because you can phrase the same question in many different ways. So at the moment, we have 4 types of questions, and you can find all the details on them in the paper. Once we finish parsing the question, we can map it to an internal query, which is very much like SQL. And this we then run on the network database. The network database maintains the forwarding state, so forwarding tables of the network, and the traffic statistics. At the high level, you can think of it as a big table containing a lot of paths, per router and prefix at least one path, and each path is associated with a few feature values. So we have, for example, the destination, so to which organization the prefix belongs to, the ingress, the egress, and the average bandwidth occupied by this path. Now, in the summarization, we try to, from all this data, extract a few groups that describe well all the data. So we try to cluster all these paths. So in here, for example, we could pick the group of paths which share the ingress, all the paths which have ingress Boston. And this leads us to the following cluster. In the paper, we call this cluster a path specification. And the path specification basically consists of a set of feature values. In this case, it's ingress Boston. But if we take another cluster, for example, this one, it could be ingress Boston, and all the paths follow the shortest path. Now, such a path specification describes all the paths which have those feature values. And the summary in Net2Text consists of multiple of those path specifications. So we can take yet another one and return this to the next stage. And in the very last stage of Net2Text, we simply map this abstract summary back to natural language. And this is done using a template-based approach. So we have sentences with holes, and we try to fill in those holes with information from the question of the operator and with information we got through the summarization phase. So we know the question was, how is Google traffic to New York handled? Which gives us the traffic identifier. And if we only look at the very first path specification, we see that it's ingress Boston. So we know it enters in Boston. Putting all of this back together, we get a sentence, we get the answer, the Google traffic to New York enters in Boston. So you saw the entire pipeline from question to answer. As you can imagine, the key ingredient in this pipeline is the summarization, where we go from a lot of data to a few high-level insights, where we identify some aggregates of data which are important and interesting. So in the following, let's first look at how we phrase this summarization problem. Then we look at two optimizations to make the summarization problem actually scale. And in the end, we'll look at the performance of Net2Text and what some operators thought about it. So let's start with the summarization. If you're just presented with the task of describing the data in natural language, it's quite easy, because you could say traffic is being forwarded. So this sentence covers or describes the data, but doesn't provide you a lot of information. On the other hand, we could say traffic from Los Angeles for that very specific prefix, which is owned by Google, is leaving the network in Chicago and follows that path. Now this gives you a lot of information, but is very specific. So we see there are kind of two extremes. We can be very generic, describe a lot of data, but don't give you a lot of insight. Or we can be very specific and provide you with a lot of details. And this we capture with two concepts. The first concept we call coverage. So it measures how much of the data pertaining to the question we actually describe by the answer. And the second concept we call explainability, which measures the level of detail we provide in a summary. Now the two examples, the two extremes I just showed you, we can put in here easily. The first one, the generic one, in the top left-hand corner, while the very specific one in the bottom right-hand corner. However, intuitively speaking, we would like to get a summary which balances the coverage. So we would like to explain as much of the data as possible while providing as much detail as possible. So we try to find a solution somewhere in the top right-hand corner. We phrase the summarization as an optimization problem, and we use for this a score. The score is computed as follows. So for each path specification, we compute the amount of traffic which is covered by the specification, and then compute the weighted sum of those path specifications. Now in this score, we first capture the coverage by looking at the amount of traffic which is covered by the summary, And we look at the explainability by assigning higher weights to path specifications which provide more detail. However, if we simply use this as a goal and say we want to find path specifications that maximize the score, it would still be very easy to find a solution, a good solution to this problem, but it would not be useful because we would basically pick the top right-hand corner and explain all the data in natural language. Now, this is simply mapping the data from one representation to another, and we don't help the operator at all. So we somehow need to be able to restrict the size of the summary. And this we do by allowing the operator to tell us how big of a summary she wants. So we rephrase the goal to being find k path specifications of size at most t. By this, we restrict how many path specifications we have in a summary and how big those path specifications are. Now still, as you can imagine, there are a lot of different possible solutions, and we can arrange them in a search space. If we look at the example for k equals 3, so at most 3 path specifications of at most size 3, we can start with the empty path specification, which describes nothing, and gradually expand this empty path specification. So always extend one of the specifications in it by one feature value. So on the left-hand side, for example, we extended the first specification by egress Sunnyvale, and on the right-hand side, we extended it by ingress Los Angeles. Now we can do this on and on until we have the full search space. And as you can imagine, the search space is quite big. It's exponential both in the number of path specification and in the total number of feature values. And due to the size of the search space, exhaustive exploration is not feasible. So we phrased the summarization problem as a ILP, and we quickly realized that it doesn't scale. If you're interested in this, you can find it in the appendix of the paper. And this is why we had to come up with optimizations to make this problem scale. And we do this with 2 optimizations. First of all, we approximate the best solution by reducing the search space. And second of all, we speed up the algorithm by reducing the data we work on. So let's look at the approximation. It was a bit quick when I showed you the first time the graph, but maybe you realize that there are 2 kinds of edges in this graph. The first type, the blue edges, always extends an empty specification with an additional feature value. So these edges lead to higher coverage. The summary in the end covers more data. On the other hand, we have red edges, which increase the explainability. So they always increase the level of detail provided by one path specification. However, our summaries should balance coverage and explainability. So we built a new graph, which always takes a red and a blue edge and creates a green edge, a combination of a coverage and an explainability edge, which leads to a much smaller graph, which balances the coverage and explainability and has a very nice monotonicity property. So the score of a child is always higher than its parent's score, and this allows us to greedily explore this graph by always following the most promising path. However, this is obviously, it's not guaranteed that we always find the best solution, as the best solution might not be in this reduced graph. Fortunately, we have a lower bound on the score, which you can find all the details again in the paper. In a second step, we also sample the data, and this is based on one insight. So the network traffic is highly skewed. First of all, there is skew in the traffic distribution, so few destinations carry more traffic than most other destinations, and we see a lot of repetition in the forwarding patterns. So many of the paths share large parts of the path. So the insight is network traffic, or the network data, is repetitive and contains some redundancy, combined with Net2Text, which has a problem that we have to iterate through all the data to summarize it. However, the summary in the end is at such a high level that this repetition or loss of repetition and redundancy at the lower level is doesn't give any problem to our summaries. So our summaries are at such a high level that we can get rid of some of the data, losing some of the repetition and redundancy at lower levels, which you will not see in the summaries. So let's look at how Net2Text actually performed and what network operators thought about it. So first, we'll look at the end-to-end timing from question to answer, and second, at the operator interviews. We tried to push Net2Text to its limits by asking it to explain the entire network forwarding state. So we asked the most general question, how is traffic being forwarded? And this we did, or I will show you now the results for one evaluation we did on the AT&T North America topology. So we generated the data for this, and we used 25 nodes, or the topology has 25 nodes. We have full routing tables, and the summaries in the end contained 4 features: the ingress, the egress, destination, and whether the path follows the shortest path. On the x-axis here, you see the time it took from question to answer. And on the y-axis, you see the score of the summary. And the score is normalized to the summary of Net2Text without any sampling. So it's normalized to this point. So without any sampling, it took us 1.5 minutes to answer the question in this scenario. With sampling 1 in 10 or 1 in 1,000, we get to much better times. So 1 in 1,000, we're below 1 second, and within 96-97% of Net2Text without any sampling. Now, this doesn't tell you very much without any comparison. So we also implemented a greedy heuristic to compare Net2Text to. This greedy heuristic iterates through all the data once, and then picks the largest data aggregate and forms a summary which is of the same form as Net2Text would produce. And we see the greedy heuristic is fast. However, it does not produce summaries with similar scores as Net2Text. And sampling has a high impact on the score of the summary. However, also Net2Text is not resilient to any sampling rates. So in this graph, I'll show you on the x-axis the sampling rate, and on the y-axis, again, the same score as before. And we see that Net2Text, up to a certain sampling rate, is quite stable, but drops significantly after, in this case, 1 in 5,000. However, this also depends on the underlying data. Now, as a last point, we also talked to a few operators to see what they think about Net2Text. In general, the network operators saw a big value in Net2Text and similar systems when they can speed up their work, if they can take away some of this time-consuming data crunching tasks. In addition, they liked the natural language interface and saw a special value for higher level management or less technical people. Also, they saw applications, for example, for customers to kind of ask what is going on in the network. Operators themselves actually don't mind the query languages that much because they said they're used to it. However, it's always difficult if a new query language appears or to get used to new features in a query language. On a second thought, the operators still thought it's not that good to have natural language because they didn't like the fact that much that the higher level management knows what actually they're doing in the network. The last part, and almost at the end, so we also asked them about the questions. They said the questions we currently support are relevant, and we saw that among the different network operators, so ISP, enterprise, network, there are different questions they would ask. So they have different requirements for the questions. So to conclude, I showed you Net2Text, a system which answers the operator's question about the network forwarding state. The answers which Net2Text provides try to balance the coverage, so the amount of data which is described in the answer, and the explainability, so the level of detail provided by the answer. And Net2Text does this in a timely manner. So before I let you go, or before NSDI lets you go, think about this question. If the network can answer your question, what would you ask the network? Let us know. Visit our website, leave some feedback, and thank you.
Questions?
Hi, I'm Shankar from AT&T Labs.
Yes.
Really cool work. I like the way you sort of approach the problem. One key aspect to the way you solve it is basically the grammar that you use to define, the parser, right? So I was wondering what kind of grammar did you choose, and what kind of flexibility does it have to extend to a larger query set beyond the ones that you already have implemented?
So James Mickens would be very happy. At the moment, there's no machine learning involved. So it's a parser which is a rule-based parser. So you can easily extend it, but the problem is if you want to rephrase or if you have spelling errors, the parser will not be able to understand your question. But there it's more the question of moving to a more sophisticated parser. On the other hand, the system should not be reduced to the parser, right? We can also skip the parsing and go directly to the query language if you prefer this. However, the parser, yes, is a nice feature for high level or less technical people, or if you prefer not to learn any query language.
Thanks.
Hi, really interesting work. So one of the important aspect of this, the network database. So I wanted to ask, like, how did you actually collected the data and what data did it incorporate? Thank you.
Yes, so this is a very good question because at the moment, this work does not look at how we get the data. So the assumption is we have the data available and we know that this is a huge problem also from the experience from us with dealing with some network operators to get this data. So at the moment, we assume that we have the forwarding state of the network and the traffic statistics. There's some work, for example, Libra, which looked at getting consistent snapshots of the forwarding state, but this is still quite an open problem.
Hey, Ajay Mahimkar, AT&T.
Yes.
So a lot of operator queries can be based on either network element IDs. So say this router in New York, NY1234, or they might use regular expressions to query for specific network entities. Right? Have you considered any of that in your natural language parsing?
So yes and no. In the query language after the parsing, we support regular expressions. But in the natural language parsing, we're a bit limited in what kind of regular expressions we support. So we support, yes, for example, you can think of hierarchies, right? You can say all routers in New York, and then we can be more specific. But we don't have like all routers which start with NY and what comes after. But this wouldn't be such a big issue to add.
Cool. Thanks, Rüdiger. Yeah.